Hello everyone, welcome to our introductory session. This is session 1 of our 11-part course for Big Data and Hadoop. My name is Anjana and I'm part of the team here at KnowBigData. I'll take a few minutes of your time to take you through what to expect of the session and to introduce you to KnowBigData. Please make use of this time to send me a quick one-liner introducing yourselves. So the session is about 3 hours long. The first half will focus on what big data is and why it is relevant in today's world. And the second half on Hadoop architecture. There will be a 10-minute break, about an hour and a half into the session, that is at 10 p.m. IST. Please use the chat window that you'll see on the GoToWebinar tool to introduce yourselves and for any queries you may have. This will be your primary mode of communication with the instructor for this session. Since it's an introductory session, what we do is we keep this open to people and have a lot of attendees, which is why everyone is muted. So our instructor will read out a question before answering it, and he will do his best to answer all the queries that are posed here today. You can help the instructor greatly by responding, by sending in your messages, keeping your messages short and avoiding chat languages. He will be able to respond to more queries that way. For those who will be joining us for the rest of the course from the next session, we'll be using a different tool which will be more interactive. For those making notes, you can sit back and relax. We will be mailing this presentation and recording to everyone. Before introducing you to Big Data and Hadoop, let me introduce you to KnowBigData. Our primary focus is online trainings relating to big data and data sciences. Thrilled to provide our course takers with instructors who are industry experts. You will soon find out for yourselves when this session starts. As part of the course, we provide access to Cloud Labs, which is a cluster that you can use to play around with whatever you learn within the classes. This feature is unique to KnowBigData. We are pioneers here, and this is something that we are definitely very proud of. Course takers are also given lifetime access to our learning management system, which will include all the presentations, recording, assignments, and project work. You will be able to use our Cloud Labs to complete a real-life project, at the end of which you will receive a certificate which can be shared on social media like LinkedIn, Facebook, and Twitter if you wish. You will be part of our alumni group, which we like to refer to as KnowBigData, which will keep you posted of new job opportunities and will help you stay updated and connected. So let us move on to today's session. Our instructor today is SANDEEP GIRI. I will let him introduce himself and take it over from here. Have a great session.
Hello everyone, this is Sandeep Giri here, and good evening to everyone who is from India, and good morning to everyone from US. All right, so are you able to hear me clearly? Is my voice feebly audible? Great, great. All right, so everybody can hear me clearly, and let me start. Now, before proceeding further, let me introduce myself while you are introducing. And so, okay. So about me, I did my graduation from IIT Roorkee. I did in 2002, and I joined a company called DE Shaw in 2002, just after campus. And the interesting thing about my job at DE Shaw was that I built big data systems before even we called it big data. At that time, we just called it distributed computing or grid computing, and we were handling a huge data on around 10,000 nodes cluster. Now after that, I founded a company called tbits global, which where we built a document management system for large enterprises. This was a great learning as well. And then I joined InMobi for a brief period where I helped in Mobi uh, in building a big recommender engine after churning around 200 terabytes of Apache logs across for last 2 years. Now, then I joined Amazon for 1.5 years, where I built a high throughput system for Amazon.com website and using their in-house NoSQL as well as building something similar to Apache Storm. All right. So in 2014, I co-founded the KnowBigData, and we are very proud of our big data sessions. Okay, and our users, our students are really finding it helpful, and we are working very hard to make the big data trainings accessible as well as useful to all the people. Okay, so we are working hard on basically improving the content, improving our delivery mechanisms, and improving the playground. Okay, so Cloud Labs is our playground where people do experiments all the time. All right. Now, in today's session, we are going to discuss two things. First, we are going to discuss big data, and second, we are going to discuss the Hadoop architecture. All right. So, the most important thing about our sessions is the ability to answer your question. We try hard to answer all the questions by everyone. There, we might miss out on your questions. Do not worry. Just drop us an email at, at Hadoop at KnowBigData, or reach us at knowbigdata.com, or log on to our forum where there are other people, there are students, ex-students, current students who will answer your question. All right. Log on to our forum. If you go to our website, you will see in the menu itself a tab called forum. All right. Now, let me start today's session. And before I proceed further, let me try to understand your background as well. Without understanding the background, I wouldn't be able to answer your questions. So we have Yogesh. Yogesh is working at as operation engineer. Great. Welcome, Yogesh. Hi, Sarath. And yeah, please feel free to introduce you using the questions window. Okay. Please feel free to introduce yourself using the questions window. Hi, Sachin. Sachin is a senior developer working at Fidelity. Great. Great to know you, Sachin. And hi, Shravnan. Curious to learn big data and its application. Great. Great. So, curiosity is the first step towards learning something. And today's session will help you understand the direction in which you could go. All right. Hi, Shravan. Shravan works for Tata ELXI as a product manager for broadcast business. Great, great. Welcome, Shravan. Hi, Manikanta. Manikanta is from Montevideo and he's working in TCS as test analyst. Great. Welcome, Manikanta. And we have Anirbit. He's in BTech final year. Welcome, Anirbit. I hope you enjoy the session. We have Deb from SunGuard, and he's a senior DBA. Welcome, Deb. You will definitely find it useful. All right. Hi, Sneha. Sneha is working in Myntra, and Sneha, you will definitely find it useful. All right. So we have Manish, who is a pro leader in BI. Great. We have Tushar working in data warehousing. Welcome, Tushar. And hi, Jyoti. Jyoti works at Shield Square Engineering Manager. Currently, we are using Mongo aggregators for our analytics In this session, I'm looking for how can I replace it with Hadoop HDFS and what the advantages of Hadoop over Mongo. All right. So we will go, Jyoti, we will go into the details of big data first and then into Hadoop architecture. And afterwards, I'm hoping that you will have a thorough clarity on whether to use Hadoop over Mongo or not. But if it is not, feel free to drop a message on our forum. I, as well as our students, will answer your question. Okay. Shailesh here, just starting off to know more on big data and Hadoop. Currently doing masters in machine learning. Great, great. And Shailesh is from Bangalore. Hi, Kingston. Kingston is working as a consulting network architecture for a couple of MNCs. Great. Welcome, Kingston. Karthik works at Oracle on its DB product. Great. And Sarath is an IT Madras student doing MTech working on project related to cloud and big data. Great. Welcome, Sarath. You are definitely going to like this session. We have Praveen working at Philips Innovation Campus using R and Python. Want to use Hadoop now for scaling up. Great, great. That's a very smart step. Okay, and all right, we have Mukesh, who is also from TCS Montevideo and working for TCS Data Tool for telecom lead. Great. Hi, Mukesh. Great. So we have a great set of candidates, and now it's close to 30 candidates in the session. And so let's start now. All right. So first and foremost, do not worry about these recordings as well as the presentation will be shared with you, so nothing to worry about taking a screenshot or wasting your time. Just focus on the concepts. Okay, just focus on the concept. Just to keep you on ease, we try to share the content. We are not so possessive about the content. All right, and we trust all our candidates. Also, focus on the concept and focus on asking the question. All right, we try our best to answer everybody's question. All right, so try to focus on the concept and answering the question, asking the right question, and rest will follow automatically. Right. Great, great. So let me just start by asking you a question instead. So what exactly is big data? Just feel free to put on your thoughts, whatever you have in mind, and then we will see where do you like. All right. So whatever is it in your mind. So what is big data? What do you understand by big data? Please, you know, put in a couple of words. All right. So you put on your words, and then I will. Okay. As per Sales, it's high volume of unstructured data that can be represented normally, that can't be represented. Okay. Big data is enormous amount of data, both structured, that was Tushar, structured and unstructured, volume variety of data, that is Ayush, unstructured data, Sachin, and it's a concept deals with huge data in terms of petabytes, that is Manish. Praveen says that big lot of information from this. Okay. We have Manikanta deals with. All right. Sneha's answer. Great. And we have Karthik's answer. Algorithm tools and processes to handle large scale of data. Okay. Right. All right. And we have Debashish, the data which is high volume veracity. All right. Collection of variety of structure and structure which can give more insights than what we can have with sampling of good. Sarath is huge amount of data like Facebook, like good, good. All right, all right. So, any more questions? Any more answers? Uh, Great. So, I have got a very, very good collection of answers from all of you. Okay. And yeah. So, great. Lots of people are actually joining now. Let me just turn off. Okay. Great. So, we have one more answer from Anand. Huge amount of data coming in high velocity. Great. All right. So, let me now. Okay. This is our definition, and this is the definition we will stick to. All right. So, first one is big data simply means data of very big size. Big data does not mean the tools to analyze big data. Okay. Big data does not mean a big data problem. Big data it just means big data, data of very big size. That's all. All right. And how big size are we talking about? The the big size which can't be processed with usual tools. Okay. The kind of data that cannot be processed with the usual tools. And to handle such kind of data, we require distributed architecture. What is distributed architecture? Distributed architecture is basically uh, using multitude of computers to solve your problem. That is distributed architecture. Okay. And the data could be of any form. It could be very well structured or unstructured or semi-structured. Okay. The difference between structured, unstructured, and semi-structured is structured means the data in where we know what are the fields in the input, what are their data types. Semi-structured means what are the we know that what are the fields, but we don't know what is their data type, such as a CSV file. Okay. And unstructured means we do not know the input format, maybe logs or maybe any other form of data. Okay. So these are the kind of data we are talking about. So the definition of big data essentially revolves around the fact that it's a huge data of very big size which you cannot process with usual tools, and it is to solve such kind of problem any tool you are going to use is going to be of distributed architecture. All right. Meaning to process such kind of product we would require multiple computers, and hence we will also require software which can run on multiple computers. Sounds good? All right. All right. Because structured unstructured does not make much of a difference. Whenever we say data means it could be in any format, right? And when we say this, data of very big size, the adjective very big does not make any sense. Second is we cannot process it with usual tools. That is also depends on what do we mean by usual, right? Therefore, out of these 4 points, the most important point and the most objective criteria is the third one, which says that big data is the one which requires you to have distributed architecture, which forces you to have multitude of computers to solve your problem. Okay. So that's what is big data. That's what exactly is big data. Now, this is the standard definition of big data given by IBM. In case people are not satisfied with this answer, the third this answer, you should give this answer. All right. Because It is sort of a definition set by IBM. They keep on adding one V every year. All right. Now, big data essentially is, let me explain the definition as given by IBM. So, it has got four V's which characterize the big data. Okay. Or let me put it this way, which characterize the data, the characteristics of a data because of which the data could become difficult to handle on a single machine. All right. So the key point will remain the distributed architecture in all of our discussions. Okay. If you count all the tools, the common thing you will find with MongoDB, Hadoop, Cassandra, and all the components which lie under Hadoop or other solutions, the common thing you will find is that they all work on distributed architecture. All the paper published by Google onto big data, they all deal with distributed computing, right? The distributed architecture using multiple computers to solve your problem, right? Now, so big data could be big by virtue of the volume, velocity, variety, or veracity. Volume means the data at rest. Imagine you got hundreds of terabytes of data. To store hundreds of terabytes of data, you cannot store it in a single hard disk, right? You would have to have multiple hard disks. So, by virtue of volume, the big data became big. Similarly, we have got velocity. So, in case of velocity, you have got so many requests coming in from the user that you cannot handle all of those requests by using one computer. You require hundreds of computers to respond to these users. Imagine Amazon getting a lot of requests from users. So, that requires distributed computing. And that's when the moment our usual architecture of single node, single server things are no longer valid, can no longer suffice to the traffic we are handling, then we call it, by virtue of the velocity in our data, we need a bigger architecture. We need a big data architecture, or we need distributed computing. Perfect. Now, the third one is variety. Okay. So, any of these four characteristics of your data can make your data big data. All right. Either volume, velocity, variety, or veracity, or more than one characteristics. Perfect. Now, imagine that let me take a case for volume. Volume is standard. Everybody knows when you have thousands of terabyte of data, where would you keep the data? Okay, you will have to have multitude of computers connected to a network, and then you store portion by portion into these multitude of computers. Now, similarly for velocity, imagine that you have got a website where you are essentially counting the hits. You have a website, you want to count the hits of the user. Now this website counter is basically a generic application which hundreds of websites are using. Now imagine that this software, the website counter is basically being used by hundreds of websites, and essentially per second the traffic that is coming from this website counter is in hundreds and thousands of hits. Okay, imagine you're getting 10,000 hits per second onto your website counter server, right? Now these kind of hits, the kind of hits you are getting is essentially increasing a integer number that we have got nth user, right? So the data accumulation is very small. The data accumulation at the end of this website counter is very very small, but since there are so many requests coming in from the users, require a distributed architecture so that the request do not go unanswered, or a hit does not get unaccounted, right? So this is called velocity. When there are so many of traffic coming in, although there may or may not be the volume accumulation due to these requests, right? So then we say that due to the velocity, we have got a big data problem. Due to the velocity, our data is big data. Now, the variety part, let me take an example. If you have to process a huge map, if you have to process a huge map, Google Map, for example, to process that Google Map, the data might be small. You might have got, say, 100 GB of Google Map size for a state, okay? And there is no data that is coming in. All you need to do is you have to find the path from one point to another, or you have to find top three paths from one point to another, considering the traffic, right? So if you have got few GBs of data and you want to, so you have got few GBs of data and all you want is find the path in it, okay? So even though the volume is low, there is no velocity, but by the virtue of problem you are trying to solve, or by the virtue of the uh, you know by the virtue of variety of data, right now we're trying to process the maps, tomorrow we might be trying to process the videos. By the virtue of this format of the data, our problem cannot be solved using one computer in reasonable time. That's when we say that we require multiple computers, we require distributed architecture, and hence our our problem statement is big data problem. That's when we say that our data is big data, our problem is big data problem. All right. Now, so is my voice audible to everyone? I've moved the mic little away from my mouth. So, yeah. Okay, great. Now, when we talk about veracity, all right, when we talk about veracity is something interesting, something or maybe very uninteresting. So, veracity is something called data in doubt. Okay, when you have a big data problem or you have accumulated a lot of data, just because you are not sure which data to keep, which data to disregard, then we call that due to this doubt, due to this doubtfulness, we have ended up in a big data problem. Now, why would that happen actually? Why would that happen that due to veracity, we get a big data problem? The reason is, okay, so why would that veracity happen? Say, for example, you got three sets of data. First one is the temperature data. You got the three copies of temperature data. First one from first source, second one from second source, third one from third source. Say first one is temperature data on each GPS location of the globe. Second one is the temperature data of each state, each city. And third one is temperature data temperature data of each zip code. All right. In these scenarios, you got three copies of data, and right now you are not sure whether which data set you want to keep. You would do analysis and then you will figure out this data is consistent, this data is a copy of this one, and this data is subset of that one. And then you will say that all these data, we just want to keep the first one, and rest of the one we can, you know, delete. Till then, till the point you reach that conclusion, you will be storing these all the sets, as well as you will be doing the churning to figure out which one is best. And therefore, due to this doubt, due to this veracity, we ended up having huge data, big data, which could not be handled by a single machine, right? So, any questions on these two definitions of big data? Any questions till now? Okay. So I'm assuming you don't have a question right now. So star actually meant the this fourth one is introduced in last year. Okay. So that one we have removed the asterisk notations meaning. All right. Now, what do you think? How many bytes are there in a petabyte? Okay. Sneha says 10 to the power 12. Anybody else says 10 to the power 12? Okay. Shelley also says. So just for those, 1 GB has 10 to the power 9, close to 10 to the power 9. All right. So, I mean, this is a common question. I just wanted to see. Right. So, how many bytes are there in a petabyte? So, are you guys busy in doing Google search? Good. Karthik says 2 to the power 50. And Sachin says 10 to the power 13. All right. Okay. Sneha says 10 to the power 15. Sarat says 15. Any other answers? Okay. Vikas also says 10 to the power 15. All right. So, yes. So the answer is that close to 10 to the power 15. And the right way of remembering it is that kilo, mega, giga, tera, peta, exa, zeta, iota. The mega is 1024 of kilo, and a kilo is 1024 bytes. And each of them is the multiple of 1024 of the previous one. All right. Now, and therefore, you can see that 1 petabyte is basically 1024 to the power 5, which is closer to 10 to the power 15. Sounds good? And yes, it's 2 to the power 50. You're right, Karthik. Because 2 to the power 10 is 1024, and then you have 5 more, which is equal to 2 to the power 50. Good, good. All right. So is 1 petabyte data big data? So we talked about two things. How big is 1 petabyte and what is big data? All right. Big data is some data which requires you to have distributed architecture. And 1 petabyte is a data containing 15 zeros. So 1 petabyte data is big data or not? What do you think? Okay. Karthik says not always. Saleh says definitely. Praveen says of course yes. Sarath says it's a big data. Ayush says yes. And Manikanta says not to an organization. Karthik says I can generate a single file containing all ones reaching 1 petabyte but won't classify as a big data. Okay. So Karthik says that he'll just generate the huge data, petabyte of data. But so, I mean, my question is, do you classify that as a data? If you could classify your data as 1 petabyte data, how are you going to store it? Do you want to store it? Do you want to handle it? And if so, how are you going to handle it without a distributed architecture? Depends on the scalability of one traditional DB system. So my question to this is Sneha's answer. My question to Sneha is that normally your traditional DB system handle the 1 petabyte data? Sravanan says depends on what we want to do with it, might be definitely big even if we want to do some simple regression over it. Okay, so he says that even if you want to do a very simple regression, it is still counted as big data. Now, my question to you is the first thing you do with the big data is to store it reliably so that when you want to do any kind of regression or anything, you should be able to, you know, easily process the data. Okay, so first thing, okay, you want to do is store it reliably. Tusar's point is it is big data. In this example, I can compress it to couple of bytes, right? So, Karthik, here we are talking about after the compression, if you have 1 petabyte data, okay? Here my question to you is, after the compression, if your data is 1 petabyte data, then, then, then how are you going to store it, right? Right. So we talked about whenever we need to have a distributed architecture for a certain operation or certain handling of data, then we call that architecture as big data architecture or distributed, basically a big data solution, right? So Karthik says store it in parts on multiple storage servers. Right, that is right. But to do that reliably, you have to build a distributed architecture, right? When you say multiple computers, that's when the whole process of building a distributed architecture starts, and we will talk about it in detail in few minutes. All right. Great. So the answer is yes. Most of the existing systems cannot handle it reliably. They cannot even store reliably. The existing file system, be it NAS, SAN, or any other form, it is not reliable. I'll prove it in one of the questions in a minute. All right. Now, so this is the standard diagram. I will quickly skip it. Just I wanted to show you that in 2002, this diagram shows from left to right the timeline. And on the y-axis, you see that there are two parts. One is colored and one is sort of a gray. And In this diagram, you can see that the gray one is the digital storage has expanded suddenly after 2002. Okay, in 2007, the digital storage reached to 280 exabytes. 280 exabyte is how many? How many zeros? Exabyte has got how many zeros? Anybody? 18 bytes. 1 exabyte is 1024 petabytes, and which means 18 zeros. Okay, exabyte has got 18 zeros, and 2, that means it is 3 into 10 to the power 20, right? So we have got so much of digital storage in 2007. Now suddenly there's something happened in 2002, due to which the data suddenly started exploding, and or suddenly started increasing exponentially. And when we say exponential, it means the rate of change of data was proportional to the existing data, right? And that was the point in 2002, was that is why it's called beginning of digital age. Good Karthik, good Sneha, great. Their answer was 10 to the power 18 in 1 exabyte. All right. Now, what is it that happened in 2002? First, the smartphones or the devices, the hardware started becoming cheaper, faster, and smaller. It became affordable to the masses. Okay, more and more the more and more devices started coming into the market, so that the average user had the access to it, and they kept on using it, generating various kinds of data, right? So that's the first reason. So every device manufacturer has a target of building a device cheaper, faster, and smaller. And that's what has led to such a revolution in the hardware that as of today, everybody has access to the phone. All right. Now, we are, as of today, carrying a phone which is powerful, more powerful than what it was in 2000s, what the supercomputer was in 2000s, right? As of today, the phone in my pocket is actually more powerful than the supercomputer of 1990s, right? So that's the revolution, that is the magic of technology that has happened over last decade. And the second factor which made the data, you know, expand is the network connectivity. On one hand, you have got these lot of devices available at a very affordable price, at a very small size, and they're faster than the previous devices. And on another hand, you have got this connectivity between devices, between people, and because of which every day we communicate, these devices communicate with the other person, and they generate a lots and lots of data. Okay, and be it Facebook, YouTube, WhatsApp, whatnot, they all generate a lot of data. There are a lot of sensors which keep on communicating to server. There are many cameras all across the globe. They are basically capturing all sorts of data, and storing it or transmitting it. So these are the two aspects, two reasons why we have so much of data today. First one is smartphone, and other one is we are able to have we have the connectivity. We have, as of today, everyone is having Wi-Fi, and there are 3G, 4G, and and there are, I mean, everywhere you go, you are connected. And when you're connected and you have a device which has so many sensors in it, can generate so much of data, you definitely would have a lot of data being gathered, lot of data is being processed by many kind of uh, service providers. Sounds good to you? Now, the reason why is a big data problem? What is it that makes, when the data grows, when the volume, velocity, or variety grows, what is it that hurts us? What is it that stops us from using a single computer? What is it that forces us to move to multiple computers? The reason behind it is this architecture, these four basic components, the four pillars of data processing. When we talk about a computing device, the computing device, the first and foremost important part is the CPU, right? Which everybody agrees to. Second device is RAM, and third device is disk, and fourth device is the network. All right. So when the data starts growing bigger and bigger, the first thing that becomes bottleneck is your RAM, and then you try to spill it over to the disk, and then disk becomes the bottleneck, and then you try to move it to the network, and the network becomes the bottleneck. And that's when so these four components are the basic pillars of computing, right? When you have put something in the network, you try to process it, then you try to read a lot of data from it, and that means the network will become your important aspect. So when you try to do the computation, at least one of these four components will become the bottleneck. At least one of the four components will become the bottleneck. Sounds okay to you? And whenever we talk about CPU, we talk about the number of flip-flops, the number of, you know, uh, conditions it can execute per second, number of instructions it can execute per second. When we talk about RAM here is a general word I'm using for caches, L1 cache, L2 caches, or registers. Basically, a memory from which the CPU reads and writes to. For because if it is CPU is taking a lot of time to read the data from disk, the whole computing will become really slow. So the more the data you can fit into RAM, the more it is easy to do the processing. But when the RAM is so big, say you have, if you had a RAM of 1 TB, then the only guy mostly will become your bottleneck is CPU. Okay, but the truth is, the RAM going beyond few hundred GB RAM is far more costly than having multiple computers. Okay, now there is something called disk size. So what does it mean by disk size is how much hard disk you have. Hard disk means solid state drives. So you read data from these hardware and into RAM. All right. And when these disks are insufficient, we move data to network, and then network will start becoming your bottleneck. So when we try to handle any of the big data, at least one of these four components will become the bottleneck, and that's when we will say that okay, we'll just have another hardware, we'll have one more computer to solve our problem. And in one of the examples, when we talk about Hadoop and MapReduce in second session, we will be talking about four or five different solutions where we try to first avoid making the RAM as bottleneck, then we try to avoid the disk as the bottleneck, and then we try to avoid the network as becoming the bottleneck, and afterwards we try to solve the problem of CPU becoming the bottleneck by putting a distributed architecture in place. So that is something we will discuss in session 2, into go into the various detail on the software level, on the program level, on the logic level, and right, and then we'll move on to Hadoop MapReduce. All right, great. Thank you, Shravana. Thank you for the compliment. I'm happy that you'll find this explanation good. Good. Now, These are few of the example use cases. I will just give you a brief example of each of these, and then we will move on to the next slide. So first one is a recommendation engine. A recommendation engine is based on the user's behavior. We give the user various kinds of suggestions. Okay, be it a movie recommendation, or be it if you go to Amazon, you look at people like you also bought this, who clicked on this also clicked on that. All right, so those are recommendation engines. Recommendation engines make a big data problem first. The bigger the data, the better the recommendations. All right, if I have watched only few movies and you come to meet me, and me and you have a discussion, hey, you have watched Matrix? You say, no, I don't have you watched Casablanca? No, I don't have. And then you say, oh, I haven't watched any other movie. So which means, had I watched many movies, or had there been more Sandeep Giris around, and you could have said, hey, who all have watched Matrix? And then there will be three people saying, hey, I know, I have watched Matrix. And then you say, hey, did you watch Casablanca also? They say, yeah, yeah, we have watched. Which means you two guys are similar to me. Can you tell the other movies you like? And hence, from multitude of people, you found your recommendations, right? Which means the bigger the data, the better the recommendation. The smaller the data, the worse the recommendations. All right. Also, you can look at it the other way. If on IMDb only few people are rating a movie, the if only few people are rating the movie, the average value is going to be skewed. Average value is going to be skewed, and therefore, therefore, the more the people, the more the data, the better the recommendation. And therefore, for recommendation, we try to get as much as data possible. And similarly, at InMovie, we did process a lot of data to figure out pattern. Instead of saying, see, we cannot handle 200 terabyte, let's just try to produce recommendation on the behavior of people for last 2 hours. Okay, in those cases our results would be horrible and our users will not like it. Our recommendation might say that these are the people who like this movie, the whole world likes this movie, right? Second is search quality. Search quality is an important aspect. Even if you are not into Google kind of search, you are building an enterprise level search. Like, for example, the document management system I built for T-Bits, that one required a search. We had hardly 100 GB of data. We had hardly 100 GB of data because it was a B2B solution. Okay, though the 100 GB data for them is too big a data, but for us, when we deal with big data, 100 GB is actually very small, because 100 GB can be very well handled on a single machine, at least from the storage perspective, right? Now, even for this kind of solution, we had to do a lot of analysis of the word. We had to build our dictionary of similarity. Whatever words we have, we should have all the plurals, or all the thesaurus in place, so that when people are looking for a word, the synonym of that word should also be given as a suggestion, right? So to do all of this, to build a great search quality, you have to do a lot of analysis of your data, as well as you have to do some analysis of the user's queries in past, as well as the what is user searching for. And therefore, search quality, even if your actual data is small, makes up for big data analysis. You, okay, the other reason of having being search quality becoming the important aspect is users expectation has grown up. Users no longer rely on categorizing and classifying the data. Instead, users rely on searching the data searching the data in a very strong manner. Users do not say that, hey, we can categorize it. You just give us some sort of quick three keyword search. No, users expectation is Gmail, users expectation is Google, users expectation is other kind of search engine which are available, right? And therefore user has understood that if you can't give the search really robust, it's not a hardware's problem, it's not the data, I mean, it's not something which can't be solved. People have solved it already. Okay. Now, third is sentiment analysis. Sentiment analysis means understanding the sentiment of your users. Okay. Understanding sentiment of the people towards a particular thing. Okay, say for example a movie is getting released and you want to see what is the behavior of people. Are people talking positive about it or negative about it? The most rudimentary form is finding out this keyword on Twitter kind of network, and then understanding the negative keywords and positive keywords, having a dictionary which says that this keyword is positive, this keyword is negative, and then counting these negative positive words in each of the sentences where the the brand you are trying to find out the sentiment about is mentioned, right? So you basically compute what are the negative things, negative words, how many negative words, how many positive words. You sum it up and then say this is the sentiment of people towards our brand. Okay, it's something of that sort. But sentiment analysis goes far beyond what I've just talked about a very simple dictionary based, and that we simply sum it up, right? So if i say that if I say that the movie was not bad, the movie was not bad, it's actually a plus statement. But but a simple sentiment analysis will not result in a correct one, in a proper analysis, and therefore sentiment analysis requires a lot of language processing and a lot of data churning, and that's when the sentiment analysis becomes a huge subject of big data analysis. Okay, you would require lot of computers to churn lot of data for sentiment analysis, because like with recommendation, if you have small data of sentiments, it doesn't make any sense. Ayush is not able to hear me. Am I audible to others? All right. Okay, great. Great. Right. All right. All right. Great. Now the fourth one is ad targeting, that is very specific to companies like Google and InMobi and other ad networks which have inventory of ads, as in lot of people want to display their ads, and there are a lot of people who are playing games, watching a movie on YouTube, or visiting various websites. There are so many people who can see your ads, and you have to give you have to give the best ads out of your repository based on the user's behavior and user's history, and that becomes to provide a best ad becomes one of the sentiment one of the ad targeting problem. To figuring out from millions of users which one get which ad is a very difficult thing, and that requires a lot of engineering, right? Now, telecommunications, customer churn prevention. If and these examples which I'm talking about, these are what people are already using, and these are not the only examples. There are thousands of use cases. If you go to say Hadoop's website and Hortonworks website and see who is using Hadoop for what, you will get a basic idea. Although Hadoop does not mean big data, but I've used the Hadoop's data because that was readily available. All right. Now, and if you understand why are people leaving you, you can avoid people leaving you, right? If I understand why people don't like my sessions, or which kind of people don't like my sessions, i could avoid I could avoid people signing out, and I could figure out, if I could figure that out, I will be fairly successful, right? Similar is the case with telecommunications. They are using it to understand the user's behavior based on how many calls did you make before you decided on to switching to Airtel from Vodafone. How many calls did you make? How many? What kind of customer support you talked about? And what is your general usage pattern? Where do you live? Have you shifted your location in recent time? Also, this sort of data tells you that there is that that these were the problems associated with the user, and we could rectify those problems if we could understand those, right? Second is network performance optimization. If you figure out the behavior of the pattern, behavior of the users, if you figure out the if you could fingerprint the network traffic, you could very well optimize the the network performance. Then calling record analysis is, it can also be done for various kinds of purposes, right? And these telecommunications people, they are using big data for various kinds of solutions. Now there is government, which basically does a lot of fraud detection, and there is a healthcare people, they are doing really wonderful thing using big data. And it is up to you. As of today, handling a huge data is not a difficult situation as it was in say 2005 or 2004. Okay, that time it was impossible for an average user to actually handle petabytes of data. But today, a person like me who is not really IBM is able to handle petabyte data, given the amount of hardware available, given the amount of services available across the globe. Okay, given the amount of open source software available today. And that is the reason probably everyone can actually handle big data using these new generation of tools. The only difference is the knowledge of these tools. Okay, this is a diagram which shows that how many Hadoop installations are there at which places, and Yahoo has got the most number of biggest font, and therefore most number of Hadoop installations. And then there is LinkedIn and Facebook, and then there are others. Okay, now here are few common myths, so pay a little attention to it. So most of us think that, I mean, think that big data means always means data above or in range of terabyte. Okay, the answer is you should follow what I talked about in very simple words. Whenever you have a need of distributed computing, then you say that our data is big data. Second, it's always about social media and doesn't apply to me. No, as I gave you an example of search quality, even when you're building a simple search, say you are building in your organization, you have something called, um, you know, customer issue tracking, right? In that, and you build this software for your organization, and now you want to provide search in this. Even for that kind of thing, if you're really passionate about providing your users a really state of art searching, then you would actually end up using big data kind of solution. Now third is, it will replace data warehousing. EDW is enterprise data warehousing. No, they will coexist. Distributed computing comes with a problem that most of the distributed computing solutions are not relational in nature. They are not transactional. Data cannot be very well handled by most of the big data solutions. I mean, it's logically not possible as per CAP theorem. Therefore, EDW and big data solutions will coexist happily. Okay, because for handling the transactional data, data warehouses are far superior, and most of the transactional data is actually smaller and handleable. You can handle it easily with Oracle kind of databases. It is just a buzzword. The fourth point is it is just a buzzword and there are no practical application. That's not correct. That's not correct. Why? Because I've just given you a lot of examples already, which basically proves the point that there are practical applications. And everybody, if you see your Gmail, you have got spam filter in place, you have got labels in place which are beautifully done, and there are lots and lots of engineering that could be built into the solution in order to give your user really great experience. Now, it's a new concept. No. As I talked about that we worked at hundreds of terabytes of data in 2002 at DE Shaw. And DE Shaw is a company which actually churns a lot of data. So it's not a new concept. It has been there. It is just that the technology has become accessible. The data has grown, even for a smaller user. The data is huge. Okay, he has so many photos, he has so many videos, and therefore they require a big data solution. Now next is, it is expensive. The answer is no. As if you compare it with Oracle and other solution, it is far cheaper. What is expensive right now is the people who are trained in the big data solutions. Why? Because of there is a lot of demand, but there is a few supply is smaller. Eighth is only for data scientists or is a magic? The answer is no. It's no longer a magic, and it's no longer only for data scientists. Why? Because whatever data scientists could do, they have done and they have delivered lot of algorithms and libraries to developers, to various kinds of people in the industry, so that they can use those algorithms and can generate. Say for example, Mahat has hundreds of functions, hundreds of commands, which basically you can use out of the box without actually writing a single line of code to generate, say, recommendation, to classify your data. Lot of things can be done without even knowing a single line of algorithm of machine learning or anything, right? Now, ninth one is we have enough hardware. We don't. So big data is not about hardware. The beauty is whatever hardware you have, you can actually utilize with these solutions. Most of these solutions have been built with the mindset that even a small hard disk can cater to a big data solution. Like, as an example, even the first solution which Google built, on which Hadoop is based, they actually built a solution so that they can take the old hard disk from their college and utilize that for storing the search corpus, right? Now, 10th one is most painful probably. Most of the people say we will build it when we need it. The answer is that's simply stupid. Why? Because the moment you realize, hey, we need a recommendation engine today, but the answer will be we don't have data. We did not store the data of our users on which we could have given the recommendations. Okay, 10 years later, or say 2 years later, your eyes suddenly open up and say, today I want recommendations to be given to my users, and that time you would not have the data, right? And why did not you have data? Because you did not build a infrastructure so that developer can peacefully log a lot of user behavior. Developer have no mental block of, you know, space, storage scarcity kind of mental block should not be there. Developers should know that, hey, they have sufficient disk space available, and they need to start storing the data today, so that after a few years down the line they have ample amount of information about the user so that you can improve the user's experience. Similarly, big data is about Hadoop. No, big data is just one keyword. Hadoop is a solution for that kind of problem, right? So is all right. Now, how important is it to know big data to make a fast growing IT career? Now, as you can see that there's a lot of demand as of today, and there is a reason for demand because all the organizations need to move to big data as soon as possible, right? As per Gartner report in 2014, as well as in 2015, as well as Forbes, all of them said that the biggest strategy for organizations, the biggest thing that organization could do as of today is to move to big data. Move to big data, move to cloud computing, move to other kind of distributed computing. Okay, and therefore because of that there is always a huge demand in the industry for the big data professionals. And and as you can see in the salary range, in the higher salary ranges, say 10 to 15, the number of jobs of Hadoop are far more higher than Java, right? Which means that the jobs in Hadoop are higher paying than Java. All right, so that's is a quick statistics, and you can see by yourself in Indeed.com as well as Naukri.com the number of jobs available in I mean for Hadoop and big data. You should look at the keyword and try to search there, and then try to find it, right? So now let's move ahead. So is this clear to all of you? No questions so far? All good? All right. Great, great. So you should be asking a lot of questions, and that's what we promote a lot. All right. So if you don't have question, there could be two things. I'm pretty bad at what I'm training at. I'm pretty bad at explaining, or I am so good that you have no questions. I have not. I mean, there is no questions left. So, and neither of that is possible. So please ask the questions. Now, so this was a general talk about Hadoop, where we talked about. Sorry, this was general talk about big data, where we talked about why do you need big data solutions as of today. And now let's move on to one of the solutions called Hadoop for the big data. All right. So big break is generally at 10 o'clock, and okay. All right. So okay, before I move ahead, thank you, Praveen, to bring that out. So there are other possible solutions also, such as having a Cassandra kind of database in your place, or having a MongoDB kind of a database, or other kind of solutions which are available. Though SAP HANA is also try to portray that they are able to handle big data, but SAP HANA is good for real-time analytics, and they cannot. I mean, SAP HANA is not great for huge volumes of data which is just lying there, right? For that, probably Hadoop is better, or MongoDB or Cassandra is better. All right. Now, Okay, so Shravan's question is there more value to the buzz around big data than the improvement of performance via distributed computing? Basically, the yes, I agree there is a little bit of more buzz, but that buzz is necessary. Why? Because lot of organizations have a huge inertia to move. Okay, therefore, unless there is a buzz, unless there is lot of people say that this is important, and they say it in various words, the organizations do not move, and that is why the buzz has been, I mean, it has been buzzed again and again to various organizations, and still a lot of organizations are not ready to move. Okay, although it has been proven by multiple people, including Gartners and Forbes of the world, that this is the way to go forward. Even despite of that much of buzz, there are a lot of organizations who are still in the contemplation phase. Okay, so that is why there is buzz, but that has been for the good reason. And improvement of performance via distributed computing. The improvement of performance is there, agreed, but it's more than improvement. It's making it possible to actually being able to handle hundreds of terabytes. Okay, hundreds of terabytes of data actually makes the existing DBAs shiver. When you talk about I'm going to handle, you need to handle 100 terabyte data. It actually makes most of the DBAs shiver, right? And it's not their problem. The problem is with respect to the existing solutions. So therefore, making something impossible, making something which was impossible earlier, making it possible today. It's about making it possible also more than the improvement of performance. So Dilip's question is that, but previously means 10 years or 12 years before, how people were managing big data. So not many people were managing big data, to be very honest. Only there were a handful of people. People like D.E. Shaw. We were the few people in the world who had 10,000 node cluster. Okay. Only few people had this kind of infrastructure. Google's and Amazon's did not exist that time. Okay, and that time the network was slow. Okay, such that the data which I used to churn used to come in a tape drive in a ship, because the ship was faster than the data if you do the computation. Okay, if I handle terabytes of data and I'm trying to download it over a week, it was not possible that point of time, even with the broadband. Okay, so those are the reasons why this new kind of paradigm is required. People need to learn this kind of solutions. Also, the things we did at DShaw were not as sophisticated as what Hadoop is today. Things we did at DShaw, we built custom solutions. They were on the lines of these solutions, but they were not as sophisticated as we are talking about Hadoop today. These solutions like Hadoop and Spark and HDFS and Hive and HBase, they are fairly sophisticated with respect to handling the load. All right. So I hope I am able to answer your question, Dilip. Or did I went off the track completely? Okay. Sarath, Sarath is not able to hear. Maybe there's a network problem. All right. So, so Dilip, was I able to answer your question, or did I went onto different track? Great. Now moving on. So when there is a lot of data being accumulated by a lot of people, we needed some solutions, and Hadoop turned out to be the best solution. Why? Because Hadoop was based on a paper by Google, three papers by Google. First one is for the file system. Second one is for the computing, MapReduce. And third one was for HBase. Okay. So Google file system, Big Table, and MapReduce, those three papers actually contributed. Based on those three papers, the Hadoop was designed. So there were two guys, Dog Cutting and Mike Caffarella, both working at Yahoo. And Dog Cutting and these guys were working on their own personal project of building a search engine. It was sort of their part-time project. And for that search engine project, they were really struggling with the storage. And that's the time when Google's Google file system came into play. And then they realized that before writing search engine, they need to build the storage system. And that's when they thought that they will implement Google's paper and make it public. So they built Hadoop on using Google's paper, and Hadoop as of today, it started with only two components, file system and compute engine. But today, Hadoop is a umbrella term for handling umbrella term, which basically is a suite of components which are reliable, scalable, and for distributed computing. There are close to 14 components under the umbrella of Hadoop as of today. So Hadoop has become a project which contains multiple projects. And in the beginning, it was named after a toy elephant of dog cutting's baby. I mean, dog cutting's kid was playing with the toy elephant that was called Hadoop, and that's why he named it so. And it is open source. The license is Apache. Apache is most open and friendly license. So in case you want to use Hadoop in your organization, you're free to do so. There is no obligation towards anything. Okay, so Apache license is the most flexible one. For commercial reasons, you can use Apache as long as you do not sell the product as is. If you do not try to sell Hadoop as is, Apache is okay with it. Okay, if you're bundling Hadoop with your solution, that's also okay. All right. Now, basically, it's written in Java. Why? So that it can run on multitude of devices across the globe. All right. So these are few characteristics of Hadoop, and this is what Hadoop is. Okay, it is started like a Hadoop started with a file system and MapReduce. As of today, Hadoop contains around more than 13 components under the umbrella, and we are going to discuss all those 13 components in these whole sessions of 33 hours, 11 sessions of 33 hours, and we are going to go into the details of each component. All right. Now, this is the general ecosystem of Hadoop component. Out of this, the most basic one is Hadoop distributed file system. We are going to discuss all these components plus few more such as Zookeeper, which is not mentioned in this ecosystem but is very much required when you deal with a Hadoop kind of architecture. Okay, so Hadoop distributed file system is something which we are going to discuss today. All right, as you can see, Hadoop distribution, HDFS is the basic file system, basic component on which everybody is standing. Flume uses HDFS, Scoop uses HDFS, and everybody else uses HDFS. HDFS is independent, which means HDFS can exist without other components as well. All right, now what exactly is HDFS? Why do we need a new file system suddenly? Were we not happy with the old one? right? So I will leave you with this question. So now, before we take a break, let me ask you a simple question. You'll get a 10 minutes to answer this question. You got to store 100 terabyte of movies or 100 terabyte of any data, which other people are going to access, as well as other people are going to store more movies in this storage. So you got to build 100 terabyte of movie storage or 100 terabyte of disk space so that people can store their data reliably. How would you build such kind of storage? How would you store 100 terabyte of data reliably? Okay, so that is the question to you. So okay, let's meet at 10:08 p.m. All right, let's meet at 10:08. There's a break, and till then you can actually think about the question also. All right, so you got 100 terabyte of data. How are you going to store it? That is my question to you. All right, so think about it. Think about this question. Give your possible solution. No matter what kind of questions we are talking about, you should basically come up with your own solution. All right, come up with your own solution for this. All right, do you have any questions for me before I leave? All right, then we'll take a break for 10 minutes and come back. All right, bye bye. Okay, so guys, I'm back. Are you guys back? Should I start? Great. So, so all right. So, what about others? I mean, I'm not getting the response from others. Are you guys able to hear me clearly? So, guys, you can communicate with me using questions window. All right. You can ask me a question if you want to convey something. All right. So, probably okay. So now the question to you is, let me read out few answers. Some of you have answered. So Zale says, not sure if I understood the question right. I would go for cloud storage with multiple racks for backup copy. So objective is to build 100 terabyte of storage in which people can store. Imagine that you are in a hostel and there are a lot of people who want to store movies, or you are in a community or in your office. For all these people, you want to build the storage. Okay. All right. So, Sailesh, here we are talking about how would you build the cloud storage. Okay. So, Sarat's answer is split the data into chunk and save these onto different machines. To avoid the data loss, we'll have to store the same data chunks in at least two or more machines. Good. That is a little step ahead, right? That's a little step ahead. Good, good. That's the solution, will be the final one. Probably in a cluster or even a cloud. That was Praveen's answer. All right. All right. Now, keep the number of services. Use a hash table like method. Keep number of servers. I'm reading out Karthik's answer. Keep a number of servers. Use a hash table like method to assign a particular file to a particular server. Excellent. Excellent point, Karthik. Example, movies can be hashed alphabetically or using their IMDb ID. Good. And yeah, brilliant. So, yeah, so Karthik is saying that keep an index of files and distribute the files across the clusters. Great, great. And maybe I can make 100 into 1, basically take 100 1 terabyte hard disks and store them in different systems. Good. That was Debashish. We will discuss this solution. Now, cloud storage is the answer from Sneha, but the question is we want to build this cloud storage. You are the engineer who is responsible for building that. Okay. So Salish's question is, how are we planning the entire course span? Will it be fortnightly? It will be actually on every weekend. It will be on every weekend. There will be two classes, each of 3 hours. Okay. And the course is starting on 24th of this month. This is a free session, and there are some student also who are basically part of the who have already enrolled, and they are also attending this first session. Okay. Now, movies can be okay. Karthik's solution we have covered. We have Sachin said I would say store in 10 hard disk in a cluster. Okay, so do you mean to say each hard disk will be of 10 terabyte size, Sachin? Mukesh's question is, connect main server with virtual machine and segregate the data. Okay, great, great. Anybody else who has who wants to contribute to the solution? Yes, Vikash, Yogesh, Tushar, Shyam. So we have 23 people in the session, and mhm, okay. So Shravanan's answer is that I could try to distribute storage like others have suggested. Could use 101 terabyte servers with indexing. Could a storage server like Stillings from Aberdeen 8RU rack be used? Yeah, that could be used, but that is probably looks like a little costly. But I don't know what is this. I'll have a look at it. Right, right. Good, good. So, all right. Some of you have given a solution like this. You took 101 terabyte hard disks and make 100 subfolders to mount these hard disks. Okay. How? You build a network, connect, put these 100 hard drives into various computers, and use network file system to make these drives available in the network. And now you mount as in you map these drives to the folders. Each of the drive will appear as a subfolder to this main folder. So you've got this main folder under which there are 100 drives. Okay, and for the sake of argument, for the backup of each drive, we keep one more drive on which we keep on mirroring the data on one drive. So on the same machine, we keep another drive. So effectively, we are using 200 hard drives to provide 100 terabyte with a duplication of 2x. Okay. Now, all right. So basically, N NAS or SAN is basically network attached storage or storage area network. All right. So basically, we am trying to build. That's the Karthik's question. Basically, here we are trying to build a sort of a network storage. Now, question is that although this is also a distributed computing kind of thing, but do you think is it reliable? What are the problems associated with this architecture? Okay. Did you understand the problems or should I explain again? So should I explain this architecture again? Right? All right. So the solution, this solution which I'm trying to give you as the first step says that we took some computers, say we took 20 computers, and we bought 100 hard drives. Okay, we bought 100 hard drives, each of 1 terabyte size, and we put 5 drives in each of these computers. So we have 20 computers, 5 drives in each, 100, that's 100. And then we connected these all computers to our local LAN via network cable. Now, and we turned on network file system on each of these machines so that all of these hard drives are available in the network to other computers. And now we built a folder structure, okay, on one of the computers first, and then mounted means mapped, okay. Whenever you are inserting a floppy drive, it is mounted as a folder generally in Unix. So or whenever we insert a hard drive, it's basically a folder onto the local drive. But we can, when you have a network file system, you can actually on a remote machine you can mount are remote hard drives. All right. So that's the kind of model we have created. And now we start storing our movies in drive 1, drive 2, drive 3, drive 4, and so on. Movies with A will go in for drive 1, movies with B, starting with B, will go in drive 2, and so on. Do you think there is a problem with this architecture? If I store one movie in drive 1 and drive 1 gets corrupted, the whole movie is lost. Very good point. That is Shravana. Okay. There is no way of recovering. That's very good point. Could you maximize the slide? Okay. If I now can you see Karthik? Sarat's point is I think network traffic will be more. Very good point. Okay. Any other? Make sense to you? Anybody else? Good, good. Karthik's point is how do you decide which disk a file goes to? Good. That's a very good point. Because because say we whatever scheme we make, there are huge chances that we end up filling one drive while other drives are fairly free. Tusar's point is that if we wish to search for a movie, it might take a lot of time. Good. So basically, Karthik and Tusar both are pointing to a problem that we could actually build sort of an index. Okay, and then we could we could keep track which movie is where, as well as we could balance the storage. Okay, point taken. And now Mukesh is saying that access speed will be slow if the users are more. Very good point, Mukesh. That is availability. There could be more load on one drive than the other. Yes, again the distribution problem. So chance of getting one drive spoiled might be higher. Thank you, Shravnan. If the root fails, then what happens? So root is generally a simple folder, right? So basically drives will be safe. Drives are remotely mounted. So if root fails, root is basically one of the 100 drives, right? And so at least one drive has failed in that case. Okay. Scanning number of disks, that is Tusar's point, or perhaps that remains an abstraction. All right. All right. So all right. Now Kingston's point is that it is slow in data access due to network latency. Good. Partitioning alphabetically won't have proper utilization of storage. Thank you, Sneha. Very good point. And maybe there are more movies with alphabet starting with A than Q. Exactly my point. Thank you. Very good point. And then you have once 100 terabyte is achieved, no scalability need to add. Very good point, Akshay. This is something a rare which we get. So basically, what he's saying that tomorrow, if you need to increase 210 terabytes, okay, then scaling up will become an issue in this architecture. You'll have to do a lot of movement. Good. Now Dilip says that if one drive goes full, then goes to the other drive or what? Yes. So that will again become a problem because this we whatever scheme we design has to be dynamic. That scheme need to be able to accommodate the drive getting full, or it should not be an issue with the disk. The CPU processing is still in a central location. I would like to use other CPUs available at you. Yes, but if you look at it, the main folder does not provide you processing. The moment you click on drive 1, it actually starts reading from the other network location and does not hit the main folder. All right. So think about mounting remote drives, and that's all. Okay. Okay. I've got really brilliant solution and brilliant questions, and they all lie in one of these points. Okay. All right. So first one is, what about failovers and backups? Okay. That was the first question. In case In case one of the drives fails, there is no other. Even if we have a backup on the same machine, it doesn't solve a problem. Why? Because if network connectivity fails or computer burns down, then you are left with nothing. Second, how would you distribute the data uniformly? This sentence has got uh, you know, multiple points inside it. First, as Sneha says that there will be a lot of movies starting with A then Q, and on the other hand, Dilip says that the if one drive gets full, what do we do then? So there are multiple problems with respect to distribution of data uniformly, right? Now, now is this best value for money? The answer is no. Because we took the 1 terabyte hard disk or maybe 2 terabyte hard disk, there could have been 5 GB hard disk available for a cheaper price. And there could be a lot of hard disks already available in your organization. Maybe some 20 GB hard disk, 80 GB, or maybe 100 GB. You could have utilized those resources, right? Now, there is something called increasing accessibility. You have pointed to that point, saying that what happens when we have the load, one of the computers will get choked, right? And scaling out, that is something interesting. The somebody raised the question saying, what happens when our 100 terabyte gets full? What do we do then? Okay, if we have to add one more hardware, can we scale up or scale out? Scaling up means increasing the drive size. Okay, well, like we will just discard our old hard disk of 1 terabyte each and we'll start using 2 terabytes hard disks. That is scaling up. But what we require is scaling out. Can we scale out? Scale out means add more hard disk to the solution without having to worry, right? So then what do we do? Then what kind of solution do we provide in order to accommodate these problems? In order to solve these problems, what is it that we should be doing? So the answer is Hadoop distributed file system or Google file system. Google file system is not available to people. So based on Google file system, Hadoop distributed file system was built, and also known as HDFS. All right. So should I move on or is there a question on this? All right. So now let us go a little bit more into the design of HDFS. All right, let's go a little bit more into the designs of HDFS. So every HDFS cluster has got two parts. One is admin node, other is data node. Admin node is the one which keeps the index of what is where. As some of you have already pointed out that if we could build an index somewhere which has the pointer to the actual data or keeps the information a central place, then our problem is solved. So on the same line, HDFS was designed. So out of all the computers you have in the network, one of the computers designate as saying this computer is my name node. Okay, this computer is going, basically this computer is the name node, and in this computer HDFS will be storing the metadata, an index of what is where, which file is stored on which computer. While this name node does not store a single file, it's just a metadata kind of service, index kind of service. And all of the data, all of the metadata means what is the file name, what is their size, which computer is it stored, and so on, right? While these data nodes, they store the actual data. They store the actual data in, not as a complete file, but as blocks of 120 MB. Okay, so as you can see in the jar, if you break down things into smaller pieces, it is easier to fit more parts into a jar as compared to bigger blocks. So on the similar line, the idea of breaking down a file into blocks was created. Okay, so basically, while admin node keeps the index, the data node contain the chunks or the slices of the file. So a file is broken down into slices, and those slices are stored onto various data nodes. All right? Onto various data nodes. The slices are stored onto various data nodes, and these data nodes, okay, these data nodes have you know ability to move the data from one to another. These blocks keep moving from one to another based on the need. These data node not necessarily have to have big hard disks, because we have broken down the big file. Even if you are storing a Blu-ray of 80 GB, it will still have 80 into 4, which is 320 blocks, and hence it will be able to we will be able to distribute it across small hard disks, right? So the file is split into chunks of 128 MB size. Earlier it used to be 64 MB, but now it has everybody has accepted as 128 MB as the okay size. Second, it helps fitting big files into small disks. Okay, it I mean, the benefit of having blocks is it also leaves less unused space on one of the data nodes, on the data nodes, so data nodes are properly utilized. Second, when you transfer the data from one data node to another, or rebalance these blocks, I'll talk about rebalancing soon. The transfer is very well optimized. Okay, now also, the benefit of blocks is that the data is distributed. So one block of a file on one data node, second block on second data node, third in third data node. And now imagine when the user is trying to access a big file, a single computer is not being bothered. Instead, user is bothering one computer for some time, then another, and hence the data is the load is distributed across the cluster. Sounds cool? Sounds good to you? Any questions on this? All right. So basically, there are benefits of breaking down file into blocks. So we talked about master slave architecture, then we talked about blocks, and now let's talk about replication. Each block which we discussed in the previous section, each block is replicated to multiple data nodes. Okay, each block is replicated to multiple data nodes. By default, there are 3 copies of each block, total number of 3 copies of each block, which means to store 100 terabyte of data, you will need 300 terabyte of data. Okay? Why? Because it is okay to have our disk, individual disk is not that costly, but our data is costly. The chance of failure of a disk is higher. And basically, the two copies of a block are never on the same node. If one data node fails, the lost blocks are recovered and the replication factor is again taken to 3 from other nodes. So you had one block on first node, second block on second node, third block on third node, sorry, first block on first node, copy of first block on second node, and copy of second copy of the same block is on third node. So you have got your block in these first three node, same block, three copies, right? Now if the first node goes down, to bring back the replication factor, a copy of block will be also sent to the fourth node. Now this node is not there, this node got burned down, or maybe the somebody pulled out the cable of data node 1. So the block, all the block that got lost here, they will be copied to the fourth node. Okay, so that is how it works. It's not sequential, it all depends on how much storage is available where. Sounds good? Are you guys there, or have I put you to sleep? Okay, all right, great, great. So everybody is awake and everybody is very much here. Great. All right, all right, so I've got really interesting question and I will actually answer all of these questions in a minute. All right. So let me answer for first question first. Kingston says that what if the data node 1 comes back to life again? Then what? So basically the block which is there, it will be checked against the main system, and then accordingly now now data node comes back to the life, right? Now there will be four copies of the blocks, right? So one of the block will be deleted based on based on uh, our requirement. Okay, because Karthik's question is, isn't it similar to RAID? No, actually RAID has different types. The RAID which I have studied has is like keep the disk on the same machine and keep a copy there and then. All right, here other than having, okay, so RAID is basically when you try to write to one disk, it gets copied to another disk, whatever you write, but not the block one. It doesn't have the block one, and it doesn't copy to another network computers straight away. All right, great. Now, now there are few questions which are coming. So first question is, what if admin node crashes? Thank you, Sarath. Very good question. Very quick answer to it is anything which is written to, I think one of, okay. So anything which is written on the admin node is also put onto the physical disk, onto the journal. So that a secondary node is always available and you need a little bit of figuring out. So that was something called secondary node, which basically could build itself from the metadata of name node. But soon enough, people came up with a beautiful idea called backup name node. Now, backup name node is something which is just standing next to the name node, exactly receiving all the information from data node. Whatever name node is receiving, the backup name node is also receiving. As per the HDFS architecture, each data node sends the information to two computers. One is name node and other is backup name node, which means that whatever name node has, backup name node will always have a copy of the whole data. In case the name node goes down, we can bring in backup name node and it will start working. All right. So that is the model which is there. So if data is stored in multiple node, then it will consume memory. Yes. So as I said, that in case the replication factor is 3, to store 1 terabyte of data, you will consume 3 terabyte, which means it is going to waste a lot of space, apparently. But no, the thing is, it is okay to waste the space rather than taking a risk of deleting data. And the replication factor is configurable and is configurable on per file basis also. Okay, in case one of the portion of the data is not very critical, you can bring down its replication factor to lower value. If you have, if you are okay with taking a risk, you are feeling, little courageous today, you want to keep only the default replication factor as 1, you can change that replication factor to 1. It's all up to you. In those cases, there will be only one block. In case that data node is lost, your data is lost. Okay. Now, for big file, data would be cut down as 128 MB in the same data. For a big file, not really. By default, although the Okay, okay. Let me try to understand the question by Manikanta. For a big file, data would be cut down as 128 MB in the same data node. Okay, so this cutting down of the data is done by the client who is trying to store the data. Okay, is that the point you have making? Yeah. All right. So next question from Dilip is, I can't understand concept of backup name node. Okay. All right. Let me explain that part. So yeah. So the name node has got a backup another computer which is called backup name node, and that information is told to all data nodes that this guy is your name node, this guy is a backup name node. Any information data node has to transmit to name node, it will also transmit to backup name node. Okay, so anything, the whole metadata which is there in the name node also knows about backup name node, so name node also keeps on communicating. So this name node, whatever metadata is there, generally the backup name node will have exactly metadata, and therefore it is fairly swappable with the backup name node. Now why do we do that? To make sure that name node is not our name node has a failover. Okay, so Manikanta's question is, all blocks will store in the same data node? No, it all depends on how much space is available on that particular data node. But first by default behavior is the first copy of the data will be stored on the same data node on which you are trying to copy the data from. Say if you uploaded a file today. So, okay, before we move forward, each of admin node, data node, or let's say name node or data node on backup name node, all of these are Unix processes. All of these nodes are Unix processes. All right. So you could run them on a same machine, or you could run on different machines. Now, so when you are trying to copy data to to the cluster, what will happen is the first copy of the data or first copy of all the blocks will have a tendency to store locally, second copy to the nearest neighbor, and third copy to the farthest guy. That is the general strategy name node follows when it tries to copy the data. Okay. Also, the copy between the data nodes happen directly. It never goes through the name nodes. All right. All right. So I hope I have answered your question, Devasis. That does it affect the performance as duplicate data in multiple nodes? So it should not, because the performance I believe you are pointing to when we are duplicating data. The duplication of data happens between the node, and hence it doesn't impact our general performance. Okay. So Kingston, your question will be answered very quickly. Yes. So Sarat's question is, does admin have the storage status? How much space is there on each data node? Yes. Admin node, name node has this entire statistics of each of the data nodes. And that's how it takes the decision. Okay, can you repeat the strategy of copying? Strategy of copying is when we try to copy the data to name node, okay, the first copy of the data will be on the same data node from which we are copying the data. The second copy will be the nearest neighbor, and third copy will be on the farthest neighbor in the blocks. And all of this will depend on how much disk space is available on which data node and how much data node is busy. All right? All right. Now, Kingston's question will be answered in the next session, next screen. So this is the typical architecture which we imagine, that user will come to name node and will will transfer the files to data node. Now, so do you think this architecture is correct? No, of course not. Why? Because here any file I write is going through name node, and hence the name node is the bottleneck, right? Name node, it becomes the bottleneck here. Therefore, most of the transfer of the data should actually happen between you and the data node, instead of for everything you engage name node. Name node is scarce resource. Name node is already singular. Therefore, we should be decreasing the data going through name node. So the actual architecture is this. User goes to name node, user goes to the name node, okay, and name node also talks to keeps on talking through the data node, but user, for storing the data, it directly talks to the name node, it directly talks to directly talks to the data node. Okay, so user comes to name node, says, hey, I want to read that file. Name node says, okay, here is the IP address of the data node from which you have to read, and go to the data node and demand this file, demand these blocks and that contain the file. Go to data node 2 that that has block number nth, and so on. So all of this detail, where is the file located, is handed over by name node to the user, so that user can directly go to the data nodes, right? So So basically, even the external world would know then, I mean, would be able to connect to each data node independently. All right. So Kingston, that's the answer to your question. So Kingston's question is it possible to configure the name node to influence the selection of data node based on the file type? So that selection strategy, you can actually write a configurable system onto HDFS, but that's generally not possible. There is no such configuration available. Right. All right. And all of this transfer happens over TCP/IP. All right. Now this is another diagram representing the same thing, where there is a name node which has lot of metadata. It has name of the file, it has number of the replicas, it has the size of the file as well, and similarly also where is what are the number of blocks available, which where are those blocks located on the data nodes. And when the user comes in, the client first goes to name node, find out all the metadata, and then it goes to data nodes which contain those blocks and start reading. And when we say client, it does not mean the you as a user will be rummaging around the blocks. No, it's the Hadoop client, Hadoop driver client, which provides you all of this functionality. You will be dealing in terms of files, saying, give me this file or store this file, and rest of this dynamics will be taken care by Hadoop client. Sounds good to you? All right. Now this is another diagram representing the same statistics. So HDFS client comes to write a file. It goes to the name node, and then it goes to the data node and stores the first step is to start the creation process. In the name node it will mark that, hey, I'm trying to create this file. Okay, but name node will just mark it as dirty, saying, this is some client who is trying to create this file, so that if the next user comes in and tries to write the same file, he gets an error saying somebody else is already creating the same file. Right now, SDFS client will now name node will tell the client saying, "Ki, why don't you go to data node 2 and store the block?" Okay, and also, and so now HDFS client will go to that particular data node which was informed by name node and will start writing the blocks. Now once that is done, this data node will start copying the data to another data node. It is peer to peer. One data node copying the data to another one, and then it will also talk to another data node for making the copy of the third copy. Okay, so that will keep on happening, and once HDFS client is able to persist one copy of the block, it will confirm to the name node that, hey, I'm done with copying the one block, and data node is now replicating by themselves. Okay, now name node will mark it as permanent in the system. What happens in case HDFS client does not go back to the name node saying that this file has been committed or this file has been saved? In those cases, name node will after some time remove the temporary entry created in the second step. Sounds good? So this is like dynamics of writing to a file. Any questions here? All right. So here, okay, Kingston's question is that can you please explain the client node and HDFS client? So HDFS client is that command provided by Hadoop or HDFS to you, using which you will be talking to Hadoop. Okay. All right. And when you're talking to the system, you will be talking from some computer that is called client node. Okay. Salisy's question is how long is the time for ACK packets to arrive? So that is a standard TCP1. Okay. The whole communication happens over TCP IP and which runs on top of SSH. All right. So that's the standard TCP IP. If a data file is updated, the other two backup files will update the same. Yes. So the whole HDFS is write ahead, meaning when you write a block, when you try to modify a file, you will essentially be creating new set of blocks and you will be dropping the older blocks. If you are appending to the file instead of modifying, then you will be just creating new set of blocks and the older blocks will remain as is. All right, that was Manikanta's question. All right, so sounds good to you? All right. Now the similar diagram is for file reading. Okay, now the HDFS client comes in, opens a file. Now, second step is it goes to the name node and it says, hey, give me the block locations. Now, it gets the block location back and it opens up an input stream based on these blocks. An input stream basically reads first from one data node, then from another. In case these data nodes are busy, the request goes to the other data node containing the replica of those blocks. Okay, so this is how the file read works. This is how the file read works. Sounds good? All right, so a few more questions. First, What is it that metadata further has? Metadata is basically list of files, list of blocks of each files, list of data nodes for each block, and attributes of file such as access time, replication factor, and other details. Okay. And there is something called transaction log. This metadata is essentially stored in the main memory, while the transaction log, as in what has been, which file has been deleted, which file has been created, etc., is stored onto the disk. While this metadata is stored in the memory, and also a copy is stored onto the disk. Now, Dilip's question is how the HDFS client will know about blocks. So here, HDFS client will know about name node and say, give me XYZ file, and name node will give back the blocks which it will be reading from various data nodes. All of the details are provided by name node. Sounds good? You have enough time. We have enough time. You can ask as many questions you want. Even if you want me to explain the whole thing again, I can do that. All right. So feel free to ask the questions. All right. So no questions? Great. Which means I can flatter myself saying that I could explain everything. All right. Even though that is not really true. All right. Now, now these are the rest of the other components. Okay. These are the other components of which. So this was the basics of HDFS, what we have just discussed. Okay. And the rest of the components of Hadoop ecosystem are as follows. The first one is Flume and Scoop. They help us import the data from unstructured to HDFS, and Scoop helps us importing the structured data onto HDFS or into our database. Okay, so scoop essentially helps us import the data from our existing rdbms, while flume helps us importing data from unstructured sources, videos, apache logs, twitter data. All of that is done by flume. Flume will be covered with a decent example of downloading data from twitter. How do you do that using flume in a distributed fashion? Now, second is HBase. HBase is NoSQL database. NoSQL database, as in they could not provide the SQL Oracle kind of properties. Okay, HBase is a distributed, heavily parallelized database, meaning it can store a data which has got millions of columns and billions of rows. Okay, and its throughput is really high and the backup is really great. The only thing HBase does not provide is there is no query language provided by HBase directly. It provides you things like the way we have a big matrix and we want to change a value in a matrix. Change for this column, for this row, set the value this much, or give me the value for this column and this row. That's the kind of a very, very, very basic input output system is provided by HBase. Now, if you have to query using SQL, you have to, if you want to query either HBase or HDFS using a SQL kind of language, you would use Hive. Hive essentially converts your SQL queries into various map reduces and then gives you the results. And what exactly is map reduce? So before we move to map reduce, let's understand something called yarn. So using HDFS, we stored the data on multiple data nodes, right? Now, if you have to do the computation, bringing all the data nodes of the file, all the blocks of the file onto single computer, and then you doing the processing is inefficient. If you try to first read the whole file, then try to do the processing and put it back. Instead of doing that, if you could send your logic to all the nodes, all the nodes inside yarn, in, all the nodes which contain the data, if we could send the code to the data, then it will be great, right? We don't have to transfer all of these blocks, and that's exactly done by yarn. Yarn helps you distributing your computing to all the data nodes available in your uh, architecture. All right. And on top of yarn, we have got MapReduce and Spark, which are paradigms of dividing your computing onto multiple machine. If you have to divide a computing on multiple machine, you have to do certain kind of semantics. And that semantics is basically in the form of MapReduce. Okay, so you write a function called map, you write a function called reduce. Map is executed on all machines while reduce is done on single machine. So that is map reduce. Spark is also a similar system, but really fast one. Now further is that if you have to churn a lot of data which is stored on HBase or HDFS, you will have to use MapReduce to do the churning. Okay, and Hive basically lets you convert the queries automatically. It converts the queries into MapReduce. Okay, so Hive basically provides you the SQL interface to the data. Okay, now similar is the Pig Latin. Pig Latin basically is similar to Hive, just that the language is little bit different than SQL. And because few people realize that SQL is not doing justice for distributed computing, therefore they wrote a newer language which is really smooth, really fast, and and really easy to write. That is Pig Latin. All right. Now there is something called Mahat. Mahat is basically a component. Mahat is basically a component which contains all the functions for the important data churning. It's like a library of algorithms. With, say, for example, you have to generate recommendation, you have to classify data, as we talked about use cases. All of those libraries are available as part of Mahat. All right. Then there is something called Oozie. Oozie is a workflow engine. Okay, say you have to build recommendations. So first you will import the data, then you will run your Mahat algorithm, or you will do some sort of ETL, transforming your data to one form to another using pig or something, and then you will run your Mahat. But to do these 4 5 steps in a sequence, you will need a workflow, and that is what Oozie is. All right, that's what Oozie is. So these are the various components of Hadoop ecosystem. So other than these components, we will be discussing few more, such as Spark streaming, Apache Storm, as well as we will also discuss in detail what is Zookeeper. Okay, during our sessions. All right, sounds good to you? Okay. So Praveen's question is, can you tell what is Uzi doing again? Now, Uzi does for Hadoop what Maven or Apache Ant does for you in case of software building, right? So when you have a project, say you want to derive recommendations, right? For recommendations, first you have to download data, import that onto HDFS, transform that you import it using Flume or Scoop, then you transformed it. After you finished with the transformation, you did transformation using Piglatin, and then you basically basically ran the algorithm. So these are 4 5 steps and they are sequential steps. So these kind of things are done using Uzi. So Uzi basically connects all of these commands together, right, Praveen? Now, so that is pretty much for today. Okay, that's pretty much. You guys are not asking question. I was expecting more questions from you, and that is why I have kept at least 20 minutes for questions. So you can ask your questions as many. All right. So yeah, MapReduce is basically, so whenever you want to process your data which is located on multiple data nodes, right? One way is to you bring the whole data. I'm trying to answer Dilip's question, who is asking that can you explain MapReduce again? So I'll try to be very brief because to explain MapReduce, I would require at least 6 hours of sessions. Okay, we generally go into the very details. The next two sessions after this are dedicated to MapReduce. All right. So let me try to be little bit, again try my best to explain it in couple of phrases. So when your data is distributed across the cluster, instead of bringing that data onto multiple nodes, you want to process the data on that very node. And, and that processing which happens on the same node where the data is stored, that is called the map portion, map. Now, once the map has finished the job, the whole data is taken. The output of map is combined together, ordered by the key, and taken to one node on which the whole data is passed through your reduce function. Okay, key by key. So that is something called map reduce. It's a paradigm of dividing your logic onto multiple nodes. That is what a map reduce is. Okay, so on which components will do the data processing like data comparing, deduping, etc. That is Mukesh's question. So all of the processing when we say is actually that whole processing actually happens via MapReduce. Okay, even if you are doing deduping, you might write your Hive queries, which is like SQL or Pig-Latin. All of that will convert internally into MapReduce to do the job. Okay, what kind of solutions can be solved by Mahat? The algorithms such as Mahat has multiple algorithms. Take the first case is recommendation. Given given the user's preference, this user likes this product this much, that user like this product that much, that user likes this product that much. If you have these three columns for all the users, you can give them recommendations very quickly. So that's the first example use case of Mahat. Second is you are given a lot of classified data, and based on that you want to basically classify unclassified data, meaning you are given a lot of information on which mails are called spam and which mails are called not in spam. If you're given this data, train Mahat such that it can automatically classify the data. So you can build a classifier using Mahat. And training can be done very well using Mahat, and the learning can happen. Yeah, you're right, Praveen. You got it correct. Right. So Salish's question is, am I right to assume that some of the components in Hadoop ecosystem are in out depending on the requirements? Like we can do without something like Hive if you are comfortable with HBase or otherwise. Yeah. So if you are say comfortable with Hive, then you don't need Pigletin. That will be a better way of looking at it. But Hive will be used in case of you want to use SQL, and using Hive, you can either churn the data from HBase or you can churn the data from HDFS. All right. So, question from Praveen is that can you differentiate Mahat versus Python versus R based on functionality, not on size? Okay. So, Mahat is a library of functions, while Python and R are proper languages. Okay. Now the only thing is, using Java you can control Mahat very well, just like as if you are doing it in Python. Rest, the difference is in the size, meaning if you have to deal with hundreds of terabyte of data, neither R nor Python can solve your problem. You got to have your Mahat in place, or Mahat along with Python. I wrote most of my work, most of my map reduce in Python and Mahat. Okay, so that's what it is. Any other questions for me? And okay, so I like to give you a heads up on Cloud Labs. So because all of our students were facing this problem of running the virtual machine, and most of them did not have sufficient RAM. Okay, and also to really get the experience, because everybody else what they do is they give you a virtual machine that you can start working on. We also give you a virtual machine, but we also give you something called Cloud Labs, on which you can do SSH. You can open our systems on the browser and start working on all the services, all the tools we are talking about in this screen. Okay, in previous screen. Now, so one is this console, which is admin console. We are using something called Ambari. Okay. All right. Let me just. All right. Let me just type in the password. All right. So let me just log in as a student. So this is the admin console, which is getting loaded, and this is our. So it shows you that there are four data nodes live, and there are zero node, and this is my name node. Okay. I'm sorry. All right. Now, all right. Similarly, we have all of these components, whatever we are going to use, And this is basically cluster monitor. It shows you what is going on with the cluster. Here it shows that only 56% of the disk is busy, rest of the disk is free. This is the memory. So this is the admin panel. You don't have to modify anything, you can just observe here. Okay, and the various services, the status of what it is. So whenever you install the cluster, you generally use a tool like Ambari or other kind of tools. Okay, now let's log in onto Hue. Hue is a part of our cloud labs, and it basically lets you interact with all the components. For example, you can see the file browser. This is basically we are browsing HDFS. We are browsing Hadoop distributed file system. Okay, all right. As well as you can interact with all other services, like if you want to execute a Hive query or Piglet query, you can click on these buttons and start working. So here, all of the data is stored on HDFS. This whole data is stored on the HDFS. Okay. So the blocks and replicas and data nodes, all of that is abstracted out from the end user. Okay. All right. So there is a lot of all the complications which you might be wondering that if my blocks are there, it is going to be so complex to read write data. The answer is no, because it's all there. Third way of interacting with our servers is going to SSH and start working on that. If you're working on cloud, uh, the cloud lab, you can just log into log into our servers, either of the servers which we have provided. All of this information is anyway provided onto the learning management system, and then you can start working. All right. So here you can interact with Hadoop command line. The client with which we have been telling is Hadoop fs minus ls. So we can see the whatever we could see from the browser from here also. And similarly, if we want to upload a file, here we can simply upload a file, and this will be uploaded onto the cluster, the data nodes. Sounds good? All right. Now go through the LMS. Those who have already the students and attending this session, go through the LMS, finish the quiz, and finish the assignment, which is based on today's session. Okay, which is based on today's session, and please, okay, so finish all that assignment, and then we can, there are quiz available there. Go through the instruction documents available in LMS. When you go into my courses, you will see LMS, and okay, you can set up your own Hadoop, but that's completely optional. We have provided all those documents, details. All right. All right. Now, the slide I'm exporting, it will be available to you. And the next course is starting next Saturday. If you want to sign up, there are few seats available. You can sign up for the course. Okay. And this one is starting from, so second class onwards, you can attend from 25th of January. Okay. Okay. If you have any questions regarding the sessions, please let me know. And these sessions are on Saturday, Sunday, 3 hours, and it will be again on the same time, 8:30 p.m. to 11:30. On 24th, next Saturday, will be this session will be repeated again for rest of the candidates. Okay. Now make sure you if you, make sure you go through the cloud labs. Make sure you understand everything if you have already signed. If you have any questions, my phone number is this one, 953-899-8962, and the email ID to reach me out to is reachus@knowbigdata.com. All right. If you have any questions, please feel free to drop me an email. Okay. And right. All right. So any questions from your side? Kingston, I'll answer your question maybe later. Or can you just copy your question and send me an email because your question is too specific to your need. I'll answer your question by email. Okay. So any questions for me? All right. Great. So if you want to sign up for the full course, which is 30 11 10 more classes, and we cover all of the component. This is the course curriculum. Okay. It's a course curriculum end to end. So you can sign up for our courses. All right. You can do that from knowbigdata.com, and there you will see the enroll button, and then you can basically sign up. All right. Great then. Thank you guys. The session must I found your questions really great, and in case I could not answer your question or something happened during the session, there is if you have more doubts, just reach out to me at reachus@knowbigdata.com. Okay. You can reach out to us at knowbigdata.com. Reach us at knowbigdata.com, and my phone number is here. If you have any doubts, feel free to call me up. Okay. Just that these days I'm having the issue with my signal quality because of some changes in the network. So in case my phone is not reachable, just drop me an SMS. I would call you back. All right. Great, Karthik. I hope that you like the session. I'm happy that you like the session, and stay in touch. And even if you are not signing up for the session, feel free to ask your question on our forum. There is some No Big Data forum where there are a lot of people keep on asking questions, and we try to answer those questions. All right. Great. Great. Thank you, Sneha. I really enjoyed your questions also. And keep interacting and sign up for the forum, and then you will keep on receiving notifications as and when other people are asking questions, and I'll keep on we or our students, they will keep answering the questions. All right. Great. 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 And thank you very much. And yeah, thank you, Sandeep. I'm happy that you found session good one. Okay. Thank you, Manikant. I am happy that you found my explanations good. I'm pretty happy with that. And we strive our best to explain concept. Thank you, Manish. Okay. Thank you, Kingston. And yeah, sure. Get in touch with me if you have. Okay. All right. And yeah. All right. Thank you, guys. Thank you very much. Thank you, Sachin. Happy that you found it explanatory. Thank you, Dilip. Yeah, we will be sending you an email with the recording and the presentation by tomorrow, 11 o'clock. All right. By that time, we should be able to upload these recordings, and then you can see that. All right. Thank you, Shyam. Great. Great. All right. So stay connected. If you really like this domain, log on to our forum also. You can start asking more questions, more detailed questions, and we'll answer that. MapReduce, we will cover a lot in session number 2, 3, and 4. Okay, we will take the complex, very complex examples, problems, and break those problems into the MapReduce paradigm. Okay, it takes a little bit more time to understand how MapReduce works. Before that, we will actually discuss about what is yarn, and then we'll move on to MapReduce. All right. All right. Thank you, Dilip. Bye bye. Have a good day. So signing out now. Have a good day, all of you. Bye bye.